All right, welcome to your Unit 3 review, where this is all things rational expressions and equations. First thing we have to review is where is something undefined? Undefined is where we want to set the denominator equal to 0 and solve. So here I'm simply saying, okay, this equals 0, do a little factoring. So x, this should be minus minus. X minus 4, x minus 3. So I'm getting 4 and 3. So those are the values that if you were to put them in the denominator of the fraction, it would go to 0 in the bottom, which would be undefined. The next section here is multiplying and dividing fractions. This is an important little note over here that I want to draw attention to. Anytime you have opposite factors where there's a subtraction between them, those will reduce to a negative one as opposed to a positive one, which you are seeing in this multiplication example that's been done. I have 3 minus x and x minus 3, so those are going to negative 1. Now, I'm going to go through this division problem where I'm going to factor as I go, but I'm also going to do keep, change, flip. So the top is dots, bottom is just AM, times, and then when I flip it, I'm going to do GCF of x, and then AM in the bottom here. So I have x minus 6, x minus 6. Okay, so then, this is my favorite part, I'm going to go through and cancel stuff that's the same in the top and the bottom. So x plus 6, x minus 6, ooh, actually double whammy x minus 6, and then it looks like I'm left with x over x minus 3. So my final answer is x over x minus 3. Now, you'll notice I'm not canceling the x's. You can't cancel across subtraction. These are glued together. The only time you can cancel stuff is if it's multiplication. So like if you had 3x over 2x, let's say, you can cancel the x's because they're being multiplied by the 3 and the 2. All right, moving on to our next section here. When we add or subtract fractions, it's important to note that we want the same denominator before we can go forward. So, first example I already have done, they already have the same denominator, so I can just proceed. Notice how I am distributing the negative to each term of the 2c plus 5, though. Now over here, what I'm going to do is factor this denominator to find out what it's made up of, and then determine a common denominator by taking one of everything I see. So I'm going to take an h minus 4 as well as an h plus 4. That means that this fraction needs me to multiply top and bottom by h plus 4 in order to get a common denominator. I'm going to distribute the 2. All right, now I have common denominators, so I can add those two things together, and I get 3h minus 12 all over h plus 4, h minus 4. And then I want to see if I can simplify it from there. I'm going to factor out a 3. And what you guys should notice is that I have an h minus 4 in the top and in the bottom. So therefore, this simplifies to 3 over h plus 4. And that's my final answer. All right, moving on to complex fractions. There's a few ways to do complex fractions, but what I'm going to do is get a common denominator among all the little fractions here. So like I'm going to put this over 1, and I'm looking at the 1, x, y, and y. And I'm going to get a common denominator of xy. Now I'm going to manipulate this so every single one of those little mini fractions also has the denominator xy. that means I'm going to multiply top and bottom of this 1 as xy over xy. He needs a y. He needs an x. He also needs an x. So here's what I have so far. Now, once you have all the denominators the same, we can drop the denominators because they would simplify. And that leaves me with, I'm going to come up over here, xy plus y all over x cubed minus x. So now at this point, I have a fraction that I just want to look to simplify. So I can factor the y out of the top. And x out of the bottom. And it looks like I can factor this even further by doing a difference of 2 squares. So just lots of factoring. What you guys should be noticing then is that the x plus 1's drop out, and my final answer is y over x times x minus 1. All right, next page, we're going to look at fractional equations. You'll notice I already have the top section filled out because those are very easy, just proportions where you cross multiply. So single fraction equal to single fraction. But if it's not that, I'm still going to look to get a common denominator first. So I'm going to look here. I'm like, okay, this factors to x plus 8, x minus 8. Which means my common denominator is x plus 8, x minus 8. So then I'm going to multiply by what the other fractions then need. So like this has an x plus 8. So that's going to need, I got to do a little erase here, x minus 8. Okay, the second fraction has the common denominator, so he's good to go. Last fraction is going to need an x plus 8. Now, this is where we tend to say, when the problem equates, we can drop the base. So I'm just going to solve the numerator here, which I have x times x minus 8 plus 16 equals 1 times x plus 8. All right, now I'm going to just do some algebra here. I'm just going to do some distribution. Okay, it's a quadratic, so I'm going to set it equal to 0. And then I'm looking to factor this. Okay, so this is most of the battle here. I've gotten down to the bottom where I've teed it up, I've solved, and I've gotten x equals 8 and x equals 1. This is super duper important. You always need to check for extraneous solutions, aka where is it going to cause the denominators to go to 0, which would cause the original function to be undefined. So if I go back up here to the original, keep in mind that there's 2 values of x that I can't have. I can't have 8 because that would cause this to go to 0. But I also can't have negative 8 because that would cause this to go to 0. Look at my answers. I got 8 though. So I'm going to reject the 8 because that's going to be an extraneous solution. It's something that came about algebraically but doesn't work in the original problem. So therefore, x equals 1 is my final answer. So again, super duper important. Make sure you guys always check your solutions. All right, next section here is radical equations. Where to isolate the radical, we want to square both sides to get rid of it. And again, make sure you always check. I'm going to put another little star here because sometimes things will reject. And then we're going to move on to this page where I just have some extra problems for you guys. So starting with the first one. Suppose that Jeff can paint a fence in 6 hours. If Tim helps him paint the fence, they can do it in 4 hours. How long would it take Tim to paint the fence by himself? So I like to call this my players of the game. I'm going to list them out. I've got Tim, Jeff, and then their effort together. It said that Jeff can paint the fence in 6 hours, so I'm going to call him 1 over 6. If Tim helps him paint the fence, they can do it together in 4 hours. So together is going to be 1 over 4. I don't know Tim. I'm going to find him, so I'm going to call that 1 over x. And the idea is their individual efforts together equals their efforts together. So I have 1 over x plus 1 over 6 equals 1 over 4. And now we're back to a rational equation like what I did on the previous page, where if I were to pick a common denominator, I'd probably pick 12x just by looking at those denominators, but maybe you do 24x. That would work as well. All right, so I'm going to go through and I'm going to multiply by what they each need. So like this would need a 12, this would need a 2x, and this would need a 3x. When the problem equates, we can drop the base and we can solve the numerator. So I can drop this, and then I can solve, and I have 12 plus 2x equals 3x. Subtract the 2x, so x equals 12. So Tim takes 12 hours to paint the fence by himself, so half a day. It's a lot of work, Tim, but we appreciate your efforts in helping. All right, and then our next example here, a double radical question. So if you recall from the previous page, the steps are to isolate the radical, square both sides to eliminate the radical, solve, and then we check our solutions. So a little bit tricky when we have two radicals. So what we're going to do is isolate one of the radicals first. So I'm going to move this one over just because I think that's going to be my easiest move. So I have the square root of x plus 3 equals 3 minus the square root of x. And now I'm going to square both sides. The square undoes the radical and leaves me with x plus 3. This I want to write twice. And then I'm going to FOIL it out. All right, so if you look at my work so far, you'll see that the x's are going to drop out. Love that for myself. And then I can combine some like terms. So if I come on over here, I have 3 is equal to 9 minus 6 radical x. Okay, we're not done yet. I still have to get rid of now the other radical. I'm going to subtract the 9, so that'll give me a negative 6. And then I'm going to divide both sides by negative 6 because I want to isolate the radical. Now if I square both sides, I end up with x equals 1. Now let's see, does that work? If I go back to the original and I do the square root of 1 plus the square root of 1 plus 3, does that equal 3? Well, this would simplify to 1 plus the square root of 4, which is 1 plus 2, which is 3. So it does check. So x equals 1 is our final solution. So this type of problem with the double radical is actually now explicitly stated in the next gen standards. So maybe you'll see something like it on the final. So a little bit more complex with the double radicals, but otherwise keep in mind the single radical problems as well, which are a little easier. And no matter what, you always got to check because sometimes something might reject. All right, now the last little bit here I want to talk about has to do with our fractional exponents and then solving fractional equations. As we would have talked about in class, anytime you have a fractional exponent, it's a power over a root. And I always remembered that by the roots of the tree. Roots are always at the bottom of the tree. So when I'm looking at rewriting each of these fractional exponents as a radical, I'm like, okay, power over root. So the fifth root of z to the first, or like this. This would be the square root of a to the first. But notice how just the a goes under the radical. And if it's negative, the negative just moves it to the other side of the fraction bar, and then same thing, power over root. Going in the other direction, this is the power, this is the root. This would be x to the 3/5. Okay? So if I want to solve a fractional equation, so these are called power equations, first thing I'm going to do is isolate the term that has the exponent attached to it. So I would divide by 3 here. All right, so if I do, grabbing my calculator here, which you can't see, but I'm doing 729 divided by 3, I'm ending up with 243. Now, I want to undo this power of 5/3 by raising both sides to the reciprocal. So 3/5. Now, when you raise a power to a power, they multiply. So technically, you're getting x to the first. That's why you want to multiply reciprocals. Over here, using power over root, this is the 5th root of 243 cubed. Now, if I take the 5th root of 243, that is actually 3, because 3 to the 5th power is 243. And then if I cube it, my final answer would be 27. Now, technically, you really could just type in your calculator 243 raised to the 3/5 power, and you will end up with a final answer of 27. But I think it's worth noting why your calculator is even giving you that answer. It's due to power over root. So 5th root, and then I can take the power of 3 to it. All right, so that concludes the Unit 3 notes. Make sure you look over all the other things that I didn't cover in the video. I just hit up what I think would be the most difficult or things that you need to remember.